So, okay, welcome to our next session, which is a bit of a bigger block, but the good news is there's a very long break, probably several months to the next broad session. So we can all relax afterwards. So yeah, it's my great pleasure. First talk today. It's always funny if you have to introduce your own colleagues in a way, but Harry and I, we also share an office, and I share one with Han Ming as well. So I've got my whole office here. That's very nice. So Harry will give a talk and talk about extracting, representing causal knowledge of health conditions. So Harry, stage is yours.
Okay, thank you very much for organizing this workshop and the opportunity for me to present my very recently research work, probably just a research idea. And to be honest, I'm always struggling to justify myself as a data scientist or as a information IR science. So there's a good workshop for me to say we actually have a gap between these two topics. And today I try to bring some causality research here to see how this can fit into those gaps. And this the outline of this talk of my paper. So my paper is a presentation paper. I try to give an overview review of recently research in this area of especially myself research result here. So my research is inspired by this kind of causality knowledge, which how this kind of causality information can help develop a new generation of information system or applications. And this kind of research currently have been recognized by many researchers, which, for example, Joshua is a Turing reward scientist, and he recently gave a talk. Recently, if you don't count the lockdown, so this is very recently, last year October, he said if machine can understand the causal structure of the world, so we can develop more intelligent and high standard applications. So my personal research or the paper I write for this workshop is about how we capture or extracting the causal information from texts, especially from the web information, and how we can construct this causal information into a way machine can understand, and the machine can use it to provide useful suggestions, predictions, and other AI-oriented applications. So for example, here, if we got a sentence or paragraph talk about a phenomena, pneumonia, and if there's some keywords has a causal relation to this topic, how we can extracting it and represent it as a knowledge for machine to reasoning and provide feedback to the application. So this is the objective. So there are a lot of currently research work in those areas. So for example, the first category can be electronic health records, which focus on how to sharing or reforming this health information into a way which different organizations, different machines, different algorithms can use those data together. But it's more focused on how to use this data to do the statistics studies. The second is apply a machine learning approach to the knowledge graph data. So you represent those causal relations into a knowledge graph, and then you're using a machine learning approach working on knowledge graph data. However, you have to have many different kind of knowledge data in order to perform the learning. So that's sometimes not feasible to do. The third direction is to start to think about a way that you can provide a new framework which can represent this in a way that from a series of platform side, you can analyze and understanding those causality and the probabilities. So these works include causal probability analysis, also the probability description logic for subjective uncertainty. So this is a fundamental development which try to solve the problem in a way that underlying you have a logic which can solve these problems. And yeah, so I think I also mentioned those limitations here, and more discussions in the paper, but I won't go details here. But if you have some questions, we can discuss it later. So my research is from this foundation, and say if we can integrate causal probability, causality and probability together to describe information as a knowledge. And then later we can use machine reasoning to use those knowledge to do some prediction work or some other kind of classification or analysis tasks. So I identified 4 process here, approaches. So first, I developed a causal probability description logic framework, which you can use it to capture the terminologies, relations between the key concepts of the sentences inside the sentences. Then we can identify which part of the text are applicable to using this CPDL, causal probability description logic. Then we start to lifting the text information into this logic framework. And then we can generate a second level of probability knowledge graph to do the prediction of other tasks. So a little bit in details. So traditional discriminant logic have a T box and the A box. So T box is a terminology level. You present the terminologies, concepts. So A box is the assertions of individuals which belongs, which have a classification of T boxes, and you have relations R between individuals or instances, which depending on the expression power you want to show, you can have 5 different levels of relations, and this make your distributed logic have different levels of power to present your knowledge. So our causal probability description logic is extended by adding 2 more elements into the top, or called T box, to the knowledge base. So in the knowledge base, we also have a phi is a causal function, and the p phi is a function which can calculate the causal probabilities. So our knowledge base have two more elements compared to the traditional knowledge discrimination logic. That's a major thing we added to discriminant logic. By adding these two things, we can have a probability, we can have capabilities to define causal analysis into a function where you can define between all possible concepts which are not applicable in discriminant logic before. And you can also have a runtime probability calculations based on the phi links between different individuals in the A box level. So we actually extended the discriminant logic framework from a flat scenario into a two layers logic framework. One is a design time causal knowledge graph. So this graph based on the terminologies, causal relations, and you can lifting the information into this logic framework. And in the runtime, we have a second layer of knowledge graph. It's a probability knowledge graph based on the input. So based on what kind of input you give to the system, you can build a probability framework or probability networks into this knowledge graph. So for our purpose, which focus on the health domain, and we define this kind of disease ontologies in the T box in our knowledge base, and also causal relations on the left side. You can see we have a root causal probability, causal property, and in the causal property, we have a root causes and different causes between different concepts into it. But not all the relations in this T boxes are causal relations. Some are just a normal relation, like a diagnose to treatment to what are drugs to what is a normal relation. But the other relations here are causal relations. So most of the relation in our knowledge base are causal relations. Then we have to identify what kind of text we need to extracting those causal information. Of course, from our example, we learn from UK NHS websites about different diseases or different health conditions. Most of the section, we can certainly say, for example, symptom section or causes section are definitely the paragraph there are the information we need to lifting those causal relations. But some conclusion or some overview sections, some sentences, we need to know whether these sentences have some causal knowledge inside those general sections. So we also develop an AI model which can detect or identify which sentences are the useful sentences we require to do our tasks. So we also test some algorithms, some CPU-based algorithms, some GPU-based algorithms. Finally, we found that CNN is the best one. It's very outperformed from others. It can achieve 98 accuracy, and you don't need very deep chain of the networks. You only need 2 layers of CNN. You can achieve a very high accuracy here. So the data we learn is from the Simon Evil 2010 tasks data sets. If you're interested, you can see the references in the paper about this data sets.
Harry, sorry, I have to ask you to come to an end soon, please.
Yes, yes. So, yes. So the whole process next is just to analyze the texts, and you can from the text to capture the causal keywords and build the relations through semantic automatic semantic annotations to lifting this into a probability into this knowledge causal knowledge framework. And based on that, we can use a very classic probability calculations to calculate the probability to be inside this causal knowledge graph. So there's some data we generated based on the input and some prediction examples we do. And we also have some data evaluations on the data set we created based on NHS data websites. And also we do some clustering for the diseases and some publications on this, and some applications like a chatbot based on the knowledge we generated, and we can answer some questions from the application of chatbot application users. Actually, that's all for this position paper. So welcome any comments and also questions if you have any. Thank you very much.
So Harry, thank you very much, Honking, Harry. So yeah, round of applause. Are there any questions? Quick question, 1, 2 quick ones.
Yes, I have one question. This framework works thanks to the availability of a large amount of data already stored in some database, isn't it? Or
no, actually we don't have any data set before we start the running this platform. So the platform itself will automatically extracting the information through like a crowd application on the NHS websites. So we build crowd algorithm on how to capture the website information from NHS, and then this framework will automatically done these things from zero information, but capture the information from NHS and then lifting the causal sentences, keywords, and then generate this causal knowledge graph, and then build the probability knowledge graph based on what kind of application you want to use. So for example, if a chatbot, we can integrate this probability knowledge graph input from the chatbot. If any other application, we can take input from the different kind of application and to generate probability knowledge graph based on the causal knowledge graph, which generated the data set ourselves from ground. Yeah.
Thank you.
Thank you. Any other question? I have a quick one. So you want to detect causalities? Did I get that right? I was just wondering.
Yes. not just detect the cardinalities, but to adding cardinalities into the knowledge graph. So currently, knowledge graph, you only have general relations, but you not have the particular cardinality relations, and how to use these cardinalities are unclear.
I mean, I like that you use description logics and these things. That's very very interesting. I was just wondering. I think when you analyze text, something like rhetorical structure theory might be helpful here. If you, I don't know if you had a look at that. And there are some rhetorical parsers available. If you want to extract some more information from text, that might be something.
Yes, exactly. So I'll also take this opportunity to thank the reviewers for this workshop to give me a lot of feedbacks when they review this paper, give me a lot of new ideas, and maybe like things I can do some more exploring in the future, either future work. Definitely a lot of work still can add it to this. So this is just a start. Yeah. Okay. Thank you for the review.
So, okay, thank you very much. So some